ridiculous.
So a reminder, a week from today was our first exam in class. You do have the entire length of the class to take it, so just be aware, homework's due that day at 6:30, and the quiz is due that day at 6:30 as well. Okay. Do y'all have any questions on the homework?
Yeah, sorry, I wasn't paying attention. I'm having one hell of a time with, was it 6-6?
Okay.
And it's honestly, I've tried to, for the very first question, I've tried using that surface area from frustrum,
Uh-huh.
and I don't know what the hell I'm doing wrong.
All right. Let's see. For some reason there is it this one?
Yeah.
Yeah. Surface area when it's revolved about the x-axis. So surface area and axis of revolution, we're revolving about the x-axis, so we're integrating with respect to what, x or y? X, yeah, surface area is always with respect to the axis. And the surface area formula was what? I have to remember that for the exam.
F of x square root of 1 plus the derivative of x. AB.
Yeah, from here, we'll go from 0 to 8. All right, so, it varies how people put this stuff together, but we're going to find the derivative, square it, and then add 1 to it. So y prime, the derivative of y is 7, the derivative of y is 7. Y prime squared, I should be 49. And then add 1 to get 50. So that expression that we end up with there is what's under the radical. So here's this on the side. So we have the setup anyways. F of x times the square root of 1 plus f prime squared dx. Was this right here. So now the square root of 50 is constant. That's 25 times 2, so that's 5 times the square root of 2. Combine it with this of 10 root 2 times pi. And then we're just integrating that linear 7x plus 5 dx.
I know what I was doing wrong now.
Okay.
I was pulling out the square root of 50 out as a constant beforehand, and I was trying to
Okay.
integrate it. All hell was breaking loose.
All right. Yeah, so got it from there.
Yeah.
Cool. All right, any other homework questions? Yeah.
On number 2 of this section, I can get the surface area equals, but it's the U substitution. They do some weird, if you look at the video example, they do some weird they randomly pull a 5 of 6 out, and I don't know what's going on. I don't know why they do it. I could replicate it, but I just don't get why.
I don't know, I guess we could watch the video, or we could.
If you just look at view of the example, it's just like when they do the U substitution, I don't understand why, I guess, the like pi part comes out when you see it happen. So I could get there easily, and then I like could get the U, even though it was like kind of confusing to me. And then it was the next part. One more. Do it again. Keep going.
We're just finding the balance.
There it is. When they pull out that 7 pi of 6, I just don't get why. Or like how they knew that to pull that out. I get that it works once you do pull it out. I just don't know how you just recognize that and then pull it out.
Yeah, so it's based on their substitution. Let's see, what was their substitution? So there's 1 plus that. So
Yeah.
then the derivative is that. Okay, so what do they say here? That x cubed over 21, which was present in the original integral. So this x cubed over 21 times 2 pi, present in the original integral, is equal to du's times 7 pi over 6. That's not necessary. I don't think that's necessary at all to do.
I just didn't get that. Like I see that it works. I just didn't know how to figure that out.
Yeah,
That's really cool.
I think that's really, so yeah. Yeah, that is not necessary at all. The only thing that's necessary is to account for this 4x cubed, because you really just have an x cubed you're trying to account for with your u substitution. And if we looked at this as, if you looked at 1 plus x to the 4th over 49, if you looked at it as 49 over 49 plus x to the 4th, then we have everything over 49, so we can take the square root of that 49 out as 1/7. So that would be the constant there. So let me just mention that here. This is number 2. So if we just rewrite this, and this over 21 is a constant too, so that could be put here with this. Let's write it as x to the 4th plus 49 all over 49. I don't know, sometimes it just depends on how you look at those constants, whether it's in the way or not. I usually move them all out front just so they're not even in the way and I don't have to think about them until later. So then we take the square root of the denominator here and then pull that out as well. So we have 2 pi over 21 times 7 from the square root of 1 over 49. Integral from whatever it was, 0 to root 21 of just x cubed and then the square root of x to the 4th plus 49. So does that make sense? The square, this here we wrote as the square root of this. Oh yeah, over the square root of 49. That's 4. That's a 4. It's getting worse. Is that better? Sure. Okay, and so then here our u substitution would simply be x to the 4th plus 49. And again, we've got the derivative of this thing on the inside sitting out right here. So that's how we know a u substitution is involved. So we'll say x to the 3rd dx with our 1/4 over there. So maybe they did that 7 pi thing just so their constants out front weren't so gnarly, but it's the same idea. Once we u substitute, you'll get the exact same answer. So we'll have our 2 pi over 21 times 7, and then our 1/4 and du, accounting for the x cubed dx. And we're just integrating u to the 1/2. So I don't know, I guess it's just a matter of how you choose to approach that. But them noticing that whatever that was, x cubed over 21 times 2 pi was the same thing as 7 pi over 6 du. Like, that's not necessary at all. So, I don't know, if that makes sense, then just go with that instead. Yeah, so, you know, the MML's homework help sometimes does things a little bit different than how we do them, so just keep that in mind. I personally sometimes think that it's a little more confusing. Not all of the problems, of course, just some of them. So, whatever that's worth. And then, you know, don't forget to change your bounds in terms of u. Yeah. Does anyone have any questions about that? Does it make sense?
Can you show the answer to the first one? Yeah.
This one?
Yeah. Well, in MML it has the answer already.
Okay, yeah. So she just want me to show you the answer. (2640 pi square root of 2 units, square units). All right. Any other questions on the homework? Okay. So we left off in 6-7, looking at this work example, and we did answer part A. Labeled this part A. How much work is required to pump the water to the top of the tank and out? Remember, the formula for work involves density and gravity as constants. Involves us integrating the area function. The area is the area of the cross sections, which depends on the tank. The height is the height to the outflow. So it's h minus y. Here it's 8 minus y. All of our areas were cross sections. Therefore, we had all areas were 4 pi. H minus y was 8 minus y, so that's how we got our integral. And then we computed all of that to get that large number. Did anyone have any questions about this? So here's part B. Will it take more or less or the same work to pump the water out if the tank was only half full? We'll call that part B. And really it's just a matter of like setting that up, computing the integral, and comparing the answers. So if the tank is half full, our water level's up to 4. What changes in our work integral? The bounds, right? The area of the cross sections don't change. The height of the container, still 8, doesn't change. But notice here, if it's half full, then all of our cross sections are only running from 0 to 4. So the only thing that changes when it's half full is the bounds. I actually did not compute that, but you know, we're essentially computing that, comparing it to part A or part A, and seeing what was the question? If it's more work, less work, or the same to pump half of that water out. Does that make sense? Does anybody have any questions or comments on that? What if the tank is full but we only want to pump half the water out. What would the work formula look like?
Be the same as
Right, yeah. So the bounds change again. The thing's full of water, but we only want to pump half of it out. We only want to pump this half out. Our bounds go from 4 to 8. Everything else is the same. Okay, cool.
And that's a different number than the one above.
Not sure. I didn't compute that. Go ahead and just so we're knowing what we're dealing with. Does anybody ever use Symbol Lab?
Yeah.
Yeah, that one's pretty good too. Wolfram Alpha is, I don't know. Wolfram Alpha is good too if you don't know about that. So what were we? Let's just enter what we had in. Just compare. So the second part from 0 to 4. I'm not sure if this will do dy dx.
So just put it's the same thing.
Do what? Oh, will it do like dy or? I don't think so. I don't think it really matters.
The one I used was both.
Yeah, I don't know. Where's pi? I don't use this one very often.
You just type
Just
pi.
PI.
Capital P, capital I?
Lowercase both.
Okay, 4 pi. What was it? 8 minus what? Let's do 8 minus x dx.
I can get lowercase p.
Yeah.
Lowercase p? I don't know. It's nice because you can see this typeset with this one. I think Wolfram's a little more intuitive because you can just you can type it out. Integrate this from here to here. So just make sure it's correct. Yeah, so it's this number right here.
No, I didn't mean that. You're doing that. Yeah.
No, this one's gonna be greater than this. It has to hold like 8. 6 lower than 7, then 6.
Okay, and then we'll change that
1, 2,
from 4 to 8.
So it's pulled less distance, so closer to 8. Because this one is
And you're assuming where it pulls from can adjust.
No. It pulls up to this point. Right? It pulls to the top.
I assume it doesn't get on summer.
No, it's pulling water test. So it takes the bottom and to the top. It goes from the top to the bottom. It was from the bottom. There wouldn't be any work. It would just be grabbed.
Yeah.
Is that 195?
So now we have numbers to compare.
I can't even name.
So that's. Okay. So the next example, this one was just I guess a basic introduction. The next example, though, we deal with a surface or the shape that varies throughout, and the cross sections are varying as opposed to being fixed circles of fixed radii. Okay. So we have this trough here, and we want to find the work required to pump the water out of the trough. work. So when you're given a figure like this, we're going to look at work as that integral mass gravity integral of the area function times the height times the thickness from whatever A to B. Okay. So when we cut through here, what are our cross sections? Remember, we're doing with respect to y, so our cross sections are like that. They're all rectangles. And do this justice. The cross sections are rectangles. Whose area is just length times width. One of those things varies, the other thing doesn't. What's always fixed with our rectangles? Yeah, whatever we're calling this dimension that's extending kind of into the page, right? Whether we call that length or width, doesn't really matter. But that the 10 meter is fixed. Okay, so that's the idea. We need to work with that, but we need W terms of Y. I'll put it over here. Straight. Well, I don't know. Let's just draw a trough for the moment. So that's 1. We'll say that's a half. All right, now we're, well, supposed to be centered. It is not quite centered. Pretend it's centered. So we're just going to look at the face of that now. So we can establish exactly how does the width vary. So really, what kind of function are we dealing with? Yeah, it's a linear function, right? Our cross sections run through here. And we want to know what's the width of each cross section. So we're really just focusing on the equation of that line. Because notice just how we've always found something that's running in the horizontal direction. Want to know how long that is? It's the right function minus the left function. Yeah. So if you want to find the other equation of this line over here, then feel free to do that. But I think it's easier, instead of saying the width is the right minus the left, since it's symmetric with respect to the y-axis, because that's the way we set it up, then we can say that the width is just 2 times the right function minus 0, or just 2 times the right function. Okay, so then we have to find what is our slope and what is the y-intercept of that line. So do we know this point right here? Yeah, 0.25 and 0. What about this point? So it's the distance out from here to here, but the whole length, the top of this was 1, right? And we cut that in half. So that's 1/2, comma 1 for our y value or height. Is everybody okay with that? We need those points to determine slope and y-intercept. Okay. We'll just do this down here. Y equals mx plus b. Find the slope. So what's the slope of that line? What is it? 0.25. We have the change in y over the change in x. So you have 1 over a fourth, which is 4. Okay. And that tells us that this is 4x plus b. And then finding b just is equivalent to putting a point in. So we know the point 0, 1/4 is on the line. So b, we're gonna plug in x equals a fourth, y equals 0. We've got, we have 4 times a fourth plus b is equal to 0. So that enables us to get the y-intercept. So we'll just put it all together. All right. So that's the equation of that side of the trough, if you will. Any questions on that? So hopefully you see the comparison to what we were looking at in like 6.3 and 6.4, especially. Yeah. But as we noted earlier, we need the width in terms of y. So we're solving for x. I'll just go ahead and write this in green. Okay, so y plus 1 over 4 is what we want to look at as the equation of that line. So what are we doing with the y plus 1 over 4 equals x? Yeah, so all right, is this y plus 1 over 4 our area function? Times 10. Remember we needed the width times 10 to find the area of the cross section. But we're not even that close yet. Because is this the width of our cross section?
At that time too.
Right. Yeah, so we said all of that work was just to find that right function. But we said that the width is 2 times the right function. Okay. So we're going to take this and put it in here. Which gives us y plus 1 over 2. And that's the width function in terms of y. Okay, anybody have any questions on that? So typically there's a few steps involved in this and you got to track a bunch of different things before you actually integrate. So again, I hope you're staying organized, otherwise it's going to be difficult. Everybody good? No questions? Okay. All right, so then we need to integrate the area function, which was 10 times W. So, I don't know, kind of running out of space up there. So our area function in terms of y was 10 times the w of y, which is 10 times, was it y plus 1 over 2? Yeah, y plus 1 over 2. Okay. So there's our area function. What else do we need? Yeah, h minus y. We have the density of water, we have the gravity, we have the area function. So we just need the height function. So h minus y would be what? What was it? Sorry. No, so the width, the height is just the height that we're moving these cross sections up to the top of the tank, right? So how far would that cross section move, or that distance?
1 minus y plus 1 over 2.
Well, so the y plus 1 over 2 was just for us to measure this
That way.
distance.
That's right.
How would we actually measure this distance from here to here?
1 minus y.
1 minus y.
It's just 1 minus y, top minus bottom. So all of these cross sections, we're just focusing on that one in particular, but they're all in there. So this is just the top minus the bottom. 1 minus y, top minus bottom. Remember when we first wrote this formula down, we said h was the distance from the bottom to the top of the tank. So we know our tank is 1 unit high, 1 meter high. So that's the top of the tank minus y. So then we have our work. Mass times density of water is 1,000. H minus y, and our area function. And we integrate from where to where?
0 to 1.
Yeah, 0 to 1. And bottom to the top of the tank. Starting with our lowest cross section, ending with our highest. Okay. So are there any questions on our setup? All right. Remember, don't integrate across a product. Whatever this is. But we have 1 minus y times 1 plus y, which is the difference of squares. So then you can just integrate those as powers of y. So that is
-1.
shouldn't be negative.
Well, no, just an integral, just -1.
Oh, okay. 32,666.6 repeating, really, joules is what that should come out to be. Questions on that? Yeah.
Can you assume that all the values for equals of the annual features?
Yeah, I think typically that's how it works out. If you're ever in doubt, just check the units though. So our distances are all measured in meters. So that's a good indication. But the density of water is also given to us as kilograms per cubic meter. So if we're dealing with kilograms and meters, then yeah, typically it's work out that way. I don't know of an instance where it doesn't. I mean, I can think of other instances, but outside of this class. Any other questions on that last example? Okay. I'll let them sort that out. Okay, so how about this one? We've got a 30-meter long chain hanging vertically from a cylinder attached to a winch. Assume there's no friction and the chain has a density of 5 kilograms per meter. How much work is required to wind the chain onto the cylinder? So also just note here that the density is given to us not as, you know, this mass times, or this volume situation, but it's kilograms per meter, which is sort of this linear density. So, you know, let's draw a crummy picture here. So here's our chain. Oh no, there's our chain. It's 30 meters long, and we want to know how much work does it require to wind that up. So first of all, is the distance of lift here, is that always going to be 30? I think that's really the crucial piece to determine. No? Yes? No. It varies, right? So if we're simply talking about this chain here, and we're talking about work equals force times distance, then working with what we have, we're already given a density. So if we think about force as mass times gravity times distance, and then we think about mass as density, in this case not volume but length, right? We've got a linear density. So we're going to think about mass as density times length times gravity times distance. So I guess depending on how you look at it, whether we're talking about, I guess, d as the distance of lift, or do we talk about L as the distance of lift? But the idea is, that's kind of the situation we're working with, because we've got a linear density. But, you know, here's one cross section here. The last two examples, we said, well, here's the work. It's based on the area of the cross sections that are caused by this volume, whatever that was. There really is no volume here, because we're just going to consider this the chain as a line, and our cross sections are then just these lines as well. So we don't actually generate an area cutting through that. Okay. So what would this distance here be? 30 minus y, right? Because we know that chain is 30 meters high. This is 30 up here. Or 30 meters. So this distance that we're lifting each cross section varies, but it varies as 30 minus y. So does it make more sense to you all for that to be D or L? it doesn't really matter, but we'll put that in there, okay. So this is 30 minus y. We know we're given the density, we're given the gravity. Then the length here, we have to just view as some length in the y direction, just some thin length, dy. So that length is dy times density times gravity. So that's our integration. We have the work, force times distance. We add all that up. We'll have density times gravity integrated from where to where? 0 to 30, yeah. Our cross sections would fill from the bottom of the chain to the top, 0 to 30. $30 minus y, we're viewing that as distance of lift, and dy was the thickness. Linear. Okay. Does that setup make sense? Are there any questions on how we got that? Okay. So I'm gonna move over here. Our constant. Just to kind of round this out. Okay. Did you get that? It's 22,050. So 22,050 joules.
Test, would we have to put units?
Yeah, just, you should be mindful of the units. Probably shouldn't say, but I'm not going to be too picky about units. Okay. So then, how much work is required to wind the chain onto the cylinder? If there's a 50 kilogram block attached to the end of the chain. So just take a moment, think about that. I guess there's a couple of ways to do it. You don't necessarily have to involve an integral. So let's take like 5 minutes and see if we can figure that out.
I got worse with the super school was higher. Class, for some reason I just couldn't find like where the online classes were. That's the last year. Right. Like then, I got on. The first like 5 like assignments.
I've never been able to do
that. Because you weren't here. And then basically I'm taking zeros and all that. And then I had to do that like right before I came here or something because it was due now. This situation here, like there was like a change to the rest of it. but also I know.
Yeah. Dot plus.
Just
Should
add
we try it?
multiply this
50
times
times
Should we
6.
try it? And this D is density, right? Distance again.
So we just like plus integral of 50.
There's no like constant way that changes.
There might just be plus integral of 0 to 30 to 50.
That help make homogeneous for distance.
No, 0 to 30. And then just use on the other side. I don't know, that might be way too much.
We don't need to do another.
What's 50 times 30? 15.
So 50
That
times 90
doesn't
times
seem like
30.
enough. Wait, no, it would be 50y. So it would be. Wait, yeah.
I thought I did, yeah, I'm not sure.
What'd you
How do you just
Plus. Oh, and then times g. So
because that right there is all the
plus times
weight.
is 14,000.
That should be multiplied by 5. No, that's just the 5 for.
What?
But I also don't. You add just to that.
Yeah, this
You add,
Yeah, so how do you do that? I just did plus integral from 30, 0 to 30.
Well, emotionally, this needs to be.
we already figured out that is the worst part. Just J. And then add basically one more block, right? It's just massive block times gravity times a distance of 30. So I got 36,700.
Yeah, that's what I did. I don't know why I wrote
It
this.
seems like that's okay right there. That logic.
Yeah, that's what I did. Except I didn't roll that difference. Now it makes what's block was in the middle is times g.
Right.
It's not losing.
Yeah.
It's not losing mass.
Yeah. Good call. Yeah. No, so we would just assume that the density of that change is consistent throughout.
Okay, so, switch that back to,
So he's gonna have to.
Wait, we don't. Oh, wait, I don't have it written down. We just did 50 times 30 times 9.8. And then added it to
Okay, yeah.
what we already had.
Alright, yeah.
But not really.
Since you're still looking at you have to take all of that and add 50 to that. So that the density of the change is not correct.
we still need to be like work tested.
Yeah, but I'm
Oh, and just like
Constant that can be
because we still need to get.
Just do 55 times.
Yeah, so that would.
I wonder if they're going to finish that point during the
This and
That's awesome.
Flavored County.
But it also says catch up, so like, we're gonna systematically.
Oh, what is that? 600 to, like, tomorrow. And it's all by ear.
This,
Oh, yeah, so
this here.
We're on traffic board too. We have to do our traffic board.
The extra meter per second.
And I don't see.
Hopefully, oh no, there's like 15 columns.
So that's just like you type the answer.
My district's like super cool. Like it's like 10%.
I don't know if I'm just not.
These homeworks? Dude,
If I'm like doing them without like.
It depends.
I'm like behind, bro.
Yeah, well,
Because
it's
I
like
like
you
get
get
one
stuff
problem
in
wrong
the script,
like
right?
19
But I
times.
see from the summer, I know exactly what these sounds like. This will happen if I just keep.
What do you think you're gonna do on the test?
Not too worried. The only thing I'm worried about is when it's like cosecant squared and it's like having the half identity or like cosine of theta. You need to like with that either of these or like what the word total.
Thinking, wait, I'm sorry, I'm sick right now.
Yeah, I should have memorized those because I don't think any of them are hard to use. It's just just getting this right instead of remember that. But then you're like, yeah, we can go through this.
And you would have this right here.
Oh, what is that?
4 times distance.
Yeah, that's what he showed me. He's like, yeah, it's gonna be.
And then all.
Oh, you just put colors down.
You just need to know these two formulas and then you just do
Here's gravity.
They trigger identities or what?
This one,
Can I take a pic of this?
So you're not gonna be doing Thursday, so.
No, we just, that was for one of the previous assignments. There was a problem that kind of related to that.
Okay, so
There
the
was one
chain.
like close transfer over like probably on there over 4 equals 4 sine.
So it makes sense that
But he's
it
like,
works for the program.
Oh, yeah, no,
Did you
I know
show
that.
me?
It's because it's just one of the
1 to 3.
It is? I'm right, right? Am I right? So the chain is 30 meters long, and the density is 5 kilometers.
Yeah, I'm sitting outside of the office every time I had a question.
So like, what kind of
Every
questions
meter
are we
weighs
have
5
to use?
kilograms, right?
I
So you usually just
It was like a
5
6
times 30. and then you get-
4, maybe 6 but it was random. So it's that, but then in 7-3, it's like all that. 7-3 is all like literally all straight. So it's gonna be like that. Work.
I'm scared. I ain't scared. I'm scared.
Yeah, 6, 1, 2, 4.
like
Yeah.
6, 7 really, I'm not sure. 6, 5, and 6, 7 really.
Yeah. Concavities. My opinion.
Well, this is just like for the work one, right? Because it's traveling through.
Charlie.
But I feel like this is wrong. I feel like because
The
like
WD-40. Yeah.
work
He had a bunch of
required,
jokes.
but also maybe
I
like.
thought
Watch
H
past
just
him.
represented H. I thought it represented X.
He's teaching English.
You got both.
The guy from Friday, I just.
I'm pretty sure I overheard that.
I think we made eye contact. Couldn't really tell. Preferred it really good. I have to leave early.
Well, no, if we were,
Kind of.
hypothetically, this is adding work to with the chain.
I don't know.
Yeah, I like that. Almost this whole weekend, it'll just be.
Has a chance
I did Monday.
I don't even know in my notes.
see it all.
I just started.
This,
Yeah, it's always
I'm not gonna be able to actually work.
It takes so long.
Like it's for my friend's wedding. Like you can buy, you can stay at a 5.
No, I even have. The ones are like, he's like old school. We can't start with this. And he raised it back in
Who wants to do it?
Exactly.
He sees that.
We don't have to do any graphic.
Yeah, so when
That's so weird. We're like, just like all up in the vectors.
I didn't in Excel though once. Because like there was one
I
graph.
think Tyson's gonna have bastards, right? Usually one or two. That he doesn't really talk about, but.
Like the five. It's like the five, like the V finals. I feel
Like
like
the one
other
half.
Because he's already
There's like some other ones.
Yeah.
That sounds like a fantasy.
My teacher is literally the coolest. We like, my class is like, and they're 12:30 and it's over at 3:50. And it's like, he teaches for like an hour and then like, we'll like do homework for the rest of the time or lab. And he'll like walk around and help everybody and he's like really great. He wrote a physics problem about Skyrim. And he likes me because I understood it. And I was like, what's going on? He seems not cool.
Couple bodies thrown in there.
Yeah.
I'm so sad that we're gonna
It's just like so many. I can't get over like rules and stuff. No, I thought you were
Wait,
like,
did
I'm
he?
not
Did he?
here.
I thought it was just fine. No one's asked it.
Where do you work, Brad?
It's called Kenny Trailer Rentals.
All right, so however you think of it, I think
Good note card.
it needs to be thought of as the total system work is done by the block plus the chain. So we've already found this in part A. The work of the block, I guess, if you're looking at just that by itself without involving an integral, I guess how do we want to think about it? We just write it out. 50 kilograms is the weight times gravity times the distance. And since it's like this point in space, the block is just a point, its distance of lift doesn't vary because it's on the bottom of the chain. It gets lifted 30 meters. So that's it. I mean, that's all we have to do. That's all was necessary to calculate the work of the block. Again, notice the units. Kilograms, meters squared per second squared gives us joules. If you just had the 50 times the 9.8, then that's just going to give you a force in newtons. So we need that additional distance of lift for that point measure of the block to go up. So I don't, what was that? 14,700, is that right? Yeah. So that's the work of the block. Or both of those, from putting it all together, we have the integral from 0 to 30. Now, the 5 was constant in the part A, but the 5 was constant because that was the density of the chain. So that's unique to the chain, right? We can't put the 5 times the 9.8 out here and do 30 minus y plus 50 dy, right? Because that 5 doesn't apply to the weight of the block. So just make sure you're being careful with that. The 9.8 is the constant that applies to both. The 5 only applies to the chain. Okay. So that's if you put it all together, you could just work that integral. But we already found this part anyways.
Would you be able to say that a constant of 5? Took it out of 50 as well.
Yeah, if you took it out of 50, yeah, we could say this is 5 times 10, and we could just factor that 5 out.
So you just integrate the 10y, you just.
Yeah, right. Yeah, so when we integrate this, it's 50y, excuse me, evaluated from 0 to 30, and that's where we get our 50 times our 30. There's 50 times 30 minus 50 times 0, but that here, that's our 50 times our 30. And then, of course, we still have our gravity hanging out front, multiplying the 50 times the 30. So you get the same thing regardless. I guess it's just a matter of preference and how you choose to look at it or think about it. Okay. So let's just round this out. What would we say? 14.7. The total work was the work of the block plus the work of the chain. Is that 22,050? Yeah. So there we go. I don't have space, but that's the idea. Do y'all have any questions on that? Okay, let's introduce this and then we'll take a break. So we're going to shift our focus now to measuring pressure on a face, like the face of a dam or something. So this time, instead of concerning ourselves with the volume, like we did when we're determining work, we're just looking at the surface area initially. So how we started out with a volume, and then we said, well, you just integrate an area times a length, and or sum an area times a length, that gives us a volume. If we're looking for the pressure on this area, then we're going to think about area as the width times a length, and then that's what we'll be integrating instead. So force is mass times gravity, and then we'll break down mass once more. Density times volume. Again, we're not thinking of a volume here. In fact, we're only thinking of an area. So we want to break down volume as area times the thickness, or a length or linear measurement, however. Okay, so density times area times thickness times gravity. But just like when we looked at a volume, we kind of integrated one dimension less, where we integrated an area times the thickness. When we're thinking about an area, we want to go one dimension down and think about a width times the thickness. So this will then be our density times our area, which we'll say is width. So I don't know how we want to say that. Let's think about it. Times thickness times gravity. So maybe let's think about it as the area is the width times the length. I don't know. Length times width. But here we mean, this time, when we're talking about the length, or sorry, the width, we're looking at, just going back referencing this figure, the width is a function of y, because depending on the container, or the face of the dam, or whatever, it could change, or it could vary as we move from top to bottom. Okay. So it's kind of a similar thought process involved with calculating the work. Here's where we break it down just a little bit different because we're using different information. Okay, and so we'll write the force. I don't think I've put this in your notes, but the force again is density times gravity, integral from A to B. The width function, the width of your cross sections times the height or length or whatever we're thinking of that as. Still h minus y from the top of the dam to the cross section itself times dy. So again, w sub y or w of y is the width of the cross section. And this varies. I'll just say it depends on the face, whatever that face is, of the container, the trough, whatever. And then our h minus y, it's the same as what it was previous. That we want to think about that h as the top of the dam or container. So the similarities here are hopefully noticeable but subtle. If you look at the wrong thing, then you're going to give, if you look at area, you're going to give a work instead of a force. If you look at width, you're giving the force, right? So remember, I'll just write this up here, that our work formula was this here, A of y times h minus y, area times length times thickness. Work is the width times the length times the thickness. That's the only difference. The only difference really then is that area function for the work versus this width function for the force. Okay, so let's leave it right there for now, and then we'll take a break and look at some examples. Do y'all have any questions before we go? All right.
I like it never discusses.
All right, let's look at an example of that. We have a triangular dam, height 30 meters, base 20. Assume the water level at the top of the dam. What is the total force on the face of the dam? So it's really the same approach as to when we're looking at how much work is done, but we're paying attention to the width of the cross sections instead of the area of the cross sections. Oops, that's not a line. So let's just set it up. I mean, we can set it up however we want, but it's always beneficial to set it up so you can utilize symmetry if possible. So we'll center that point on the origin. And then so hopefully like this, a setting like this looks familiar, especially considering one of the work examples that we've done. So we're just going to write out force is density times gravity. Width function, the height function, and the thickness. So once again, our width function is measured by this distance here. what would h minus y in this instance be? Yeah, height of 30. So that's 30 minus y from here to here. For all of the cross sections we look at. Except for, of course, the one at the very bottom and the one at the very top. That's it. So again, we need to think about the width. Is that length right minus left? Or we could just figure out what the right function is. 2 times the right function. We didn't write this one down this way, but you know, we can think about that as 2 times x. Because this distance from here to here is just some x value, which varies. Okay. So now we find the equation of this line. Same way we found the other one. So I'll just label this here. Our right is that mx plus b. So b, for this one, straightforward. What's the slope of that line? What is it? 3/2. Do y'all agree? No? 3?
For y or for x?
Yeah, in terms of x. That's the point 0, 0. What's this point?
10:30.
1030? Yeah? So definitely a height of 30. Again, we've got to think about, we cut that 20 in half. So if we're over there, then that's half of 20, which is 10. So that. Did you guys get 10? Thanks. Okay. So our slope is 30 over 10, or 3. In other words, y is 3x. So we're using that to say, all right, well, the right function is 3x minus the middle, if you will, and 2 times that. So right minus 0 times 2 gives us the width of that cross section. But again, this is in terms of y, because our cross sections have thickness dy. So we need this in terms of, we need that in terms of y. Okay. Any questions on that? I think that's with these. Or the work problems, those are the key aspects setting up that area or that width function. By far the most difficult component of that integral. Okay, so then our the width of each cross section is just 2 times x. So that's 2 times y over 3. Or 2/3 y. That's it. So we have our width function, we have our height or length, whatever you want to think of that as, function. And those are the only 2 components that we needed here to integrate that, to find the force. So So we have mass times gravity, or sorry, density times gravity, integrated from where to where? Yeah, cross sections range from 0 to 30. Two-thirds y for the width function times 30 minus y dy. Any questions on that? All right then, so then what we have, 9,800 times 2 over 3, integral from 0 to 30, integrating 30y minus y squared dy. What are our units here? Yeah, newtons, it's a force. But again, if we think about the density of water, kilograms per cubic meter times gravity, meters per second squared, times the width function. What unit does the width function have? Meters. Height function, meters. dy, also meters. So we have the last 3 meters cubed canceling with our meters cubed for the density, and then we're just left with kilograms meters per second. Which is our newtons.
Second squared though? Is it second squared?
Oh yeah, second squared, yeah, thanks. All right. Numerical value of this then, rather large. 29,400,000. No questions on that, right? Move on. Okay. So I want you to try number 8.
Wait, I still have to get to that.
set up. Yeah, if you.
So if it's only one ton, you can pull it out. It's like another one,
You can take out the 5.
like,
That's cool.
2 thirds. I think we're gonna eventually.
This one is definitely.
For the setup, yeah, it's 85 something.
What's your function?
We both got 612.5.
My constant is 91.5. Yeah, you should use it out there and do that.
Basically, the form you need is just ES information, right?
No, but it's the because there's still like 4 years of production now.
Okay, so I heard so it's like 25 minus y for the price. Sure.
That's what counts.
That makes sense.
Yeah. I'm just on this. Piece off this line. See, why do you have a 2? You said 25 times this.
No, I mean, that's
But he was saying that how much water is put in something, the pressure of the surface never changes. It's whatever's on the surface. But it's whatever, if it's whatever's on the surface, it will only be counting whatever's on the window.
87.5.
They say for it. That's right.
that's squared.
I did something.
So it hasn't been like the rest of the.
Yeah, I feel like you can do this is.
I feel like Oh, yeah. Even if it's like, I guess you know that like.
It doesn't change but it also changes the way. Wait, no.
9187.5. So it would just change, so it would change the age.
Maybe this is.
And it would, that window's the same.
And I don't think it would change the bounds, because you're just pretending that
We all got the
That's not how high
yeah, so set up, so I don't, there's gonna be like 20 minutes of reuse. I got you.
What's your Confirm 4 minus 1.
4 minus 0. Okay. 4 minus 0 is the entire equation. That's right.
9, sorry, 9. I just changed it from 4 minus y to 3 minus y. And everything else is,
Why?
because 1 meter off the bottom, so 1 meter of water isn't gonna affect the window. It's just the 3 meters of it. So now it's 3 minus y times the window is the same, so 1.5.
0 to 1.5.
Like it changes the window, so it's 1 meter, so it decreases the height by 1.
Oh yeah, I don't have mine for it. So
Oh,
I didn't say that. I was like, what are you talking about? I was like, it says it's on the bottom.
Then wouldn't 0 have to be the upper limit of integration? 0 is the entire thing subtracted by the.
Okay.
0 is the entire, like.
Huh?
I think that up and then
Yeah.
I don't know, I just like
How come?
I prefer to print them. I just like to for some reason.
I don't understand it though.
4 minus 0 is the entire.
There was like one time, like for the most part, in Charles, I printed every time. And like one time I didn't print it, and he noticed. And like roasted me in the costume about it. I got roasted so hard. Like I was like, I print it every time.
His notes were really good though.
Yeah, quality.
Right.
I think these are really good too.
Okay.
like drawing it on the floor.
I did pre-cut it around. I pre-cut it.
And I was like, oh,
So it's, is it all she does?
Because I was thinking, like, you know, you're driving out with
You can set it up like that.
Okay, so basically the
Is it
balance.
still 0?
because I was my original
3 minus y?
4 minus y.
I want to do like how hard are your tests?
Yeah.
How hard are your tests?
yeah, so you see
it's just gonna be.
I just hate like the problems where you just like find like I don't know the ones that we find like the slope and everything. It's like you mess up in the beginning, one part, the whole question wrong.
As the
Hate
y
that.
value.
My teacher, my pre-calc teacher used to grade it, and even if you got your initial stuff wrong, if you still like went about it the right way after that, she would still give you credit based on that.
I think the answer like
Yeah.
no partial credit.
I switched to one top of the week with calculus.
Yeah, no, that makes
Yeah.
He's getting used to it, you know.
Is that a wrong way? I think this is much better. Yeah, it took me a while to like think and.
Fine.
Orientation.
Hack the computer. It's cute. You can hack stuff, right?
Versus like.
I love Don't climb rush. But I'll see what
Yeah, so I wasn't
Still on the slideshow.
it was possible to do it. I was just thinking like it sounded like wax.
I wish he was a teacher like that. Like, I should grab it if you're
But I
like,
think
honestly.
Charles is actually
What is the meaning of life?
If I had done it my way, I would have
only have one five.
Yeah.
I'm not big brain thing. I was still thinking of like this term.
Oh, that was. Is this like a, because that water is still calculating your words to
Technically, what I was doing.
We all like
if I was
roasted.
thinking, all right,
I feel like those same
That really skinny kid that like, I think he sounded like a really skinny
Yes,
guy.
because we're
He was like on the
Oh, yeah, yeah.
He works in the apartment complex. Yeah, I saw him like at that mailbox and someone was like,
If you want me to.
I wonder how he does.
tell you what I.
I know, I want to see everyone's grades. I know, I really want to know how Tom.
Yeah, like, let's go with Blair's.
But he's in, I mean,
That's kind of like weak brain.
so deceived that he gets decimated. I'll take him.
And now you've
They
got
lost.
Stat there.
Way that he
Oh, they have to.
Yeah, 918.
Just like, right.
Would increase any workers, which is why.
It could just be for engineering.
Okay, but
It could just be
He's
your.
a computer science major, accepted his health points for it.
the way they. Do you need high math?
Yeah.
You didn't cover this,
I don't think you use that, but you can say, I'm just like biochemistry.
Because if you said it as if like.
I don't know about that. I am cool. I am cool.
That's why I had to draw it out.
I'm cool.
Probably like upper level.
Is he gonna fix the look?
Like biochemistry, it's like the only thing I have to take all the ones where it's just pressure on the system.
Or like put them out.
What is it? You could get through all of chemistry where it's just like.
I know, like, you know, case.
Calculus physics doesn't work.
Listen, I work at Pizza Hut.
I haven't done
I'll take this.
All right. Circle back around.
I feel like health one, I health
I trust you.
But he's like, the whole teaching you because you don't have to learn.
Bubble wrap it in heavy side.
You have learned it, that part.
And if I take that for physics 1 and 2, but they're both algebra based, so when I get to college, I'm just going to learn it again. It'll be calculus based, but I'll just like breathe through the class. Because it's like,
So you're like super good at putting together.
why does the system board?
I'm sure you're great. Then you go to that school for like child prodigies. Or something, that's what it was.
Why is that the same thing as the graduate time?
They were like, we don't need lights. I'm trying to learn how to play piano, but like I can only do things with my right hand. I can't do different things with my hands. Like it's like, except for red on a whiteboard. Thank you. I can write the alphabet forwards with one hand and backwards with the other hand. In the same direction. Maybe, I don't know. Until you have it. Until you have it.
All right, I was able to make it around to all of you. That's the correct setup. Everybody had that, which is great. So did anyone have any questions on that? So remember this, I think I addressed individually, but the H is always the top of the container. The bounds are simply following the cross sections. The cross sections that you draw or visualize that's what you're measuring the pressure on. So that's how those are always configured. And this was 9187.5 newtons. 87.5 newtons. I know it's in setup, but straightforward. Okay. Yeah. So then, what would change in the second part or question 9? What changes? the height of the, where each cross-section is? Would those change?
Yeah, go
It'd just be
from
the
1.5 to 1.
upper and lower bounds of your integral.
One, so it would be the upper and lower bounds of our integral, or the height changes how?
The upper and lower bounds of the integral.
Just the
changes
upper.
from
Just H
1.5.
Okay. So yeah, does the height of the pool change? No, so H doesn't change. The pool is still 4. This time, the viewing window is 1 meter from the bottom. So that's just 1 meter. It's moved up. Again, we're measuring the force on the face. So it really depends on how you orient these things. We had a discussion, you know, if the top of the pool is actually on the x-axis, then things change, right? You have, you know, specifically we were talking about this. What if this portion right here was the x-axis, and here's our y-axis like this? Then things change depending on the orientation. But it doesn't affect the outcome. The force on that face is the force on that face, whether we look at it, you know, set up like this, or set up with the, you know, x-axis on the bottom of the pool. If we rotated that thing 90 degrees or 180 degrees, the force is still the same. It's just the setups would look different. So, you know, I would just go with setting up things how you would normally look at them. And try to utilize symmetry if you can. We didn't really need to utilize symmetry here because the width is always the same. It's always 1/2. So we didn't really need to think about, is there a defining function? The width varies. That wasn't the case. So our lower limit of integration is starting at 1 because it's 1 meter off the ground. And then still a square of 1/2. So our upper limit of integration is 1.5. 3/2.
So bounds.
So, right, just the bounds changed. This distance from here to here, let's say, that's still 4 minus y. The width is still 1/2. We'll just write this as 900. So, what do we say? Width, still half. Height of the cross sections was the same. We go from 1 to 1.5 instead. That's the difference there. Okay. And so that's 6,737.5.
So on the test, you're gonna have us like working it out or just setting it up?
Both. Yeah, both. Yeah, any questions on that? Okay. So I will say that, you know, how you choose to orient these figures, it doesn't matter, but keep that consistent when you're talking about the bounds and the width or the area and the height, right? I just you know, want to mention that. I think it's important to, because some people, depending on the shape, will look at it one way and others will look at it another way. But let's say, you know, let's say in that first part we said, all right, well, here's my pool. This is down here at -4, and my window, wherever you want to put your window. If you want to put your window here, that's fine. If you want to put your window in the top corner, that's fine too. But from the cross section itself to the top of the pool, what is that distance? Is it 4 plus y? So how would we measure this distance from here to here? The top minus the bottom, right? So the top is 0, and that's still some y value. So this h minus y is 0 minus y, or just minus y, if you set it up like that. I mean, I would say sometimes the way people set things up, I don't understand why they do that, but that's totally fine. As long as you're keeping that consistent in setting up your bounds and your area or your width or whatever, should all be the same. If we rotate this 90 degrees and we integrate with respect to x, it's all the same stuff. It's just that, you know, our height, our bounds, all that kind of stuff changes. Okay. All right, and then the last page is a summary, just a recap of this. I was calling that like height. It might be more appropriate to call this depth, but whatever. This is our h minus y. Your book labels it a. All right, that's 6-7. Move on to 7-3. So 7-3 is part of the first unit. Just make sure that it's not all just chapter 6 stuff. So in 7.3, we look a little bit at the hyperbolic trig functions. And we'll sort of see the analogy in a minute, but our hyperbolic trig functions, the two primary ones are the hyperbolic sine and the hyperbolic cosine. So this hyperbolic sine is read sinh of x. And hyperbolic cosine is read, I don't know, cosh of x. So I don't know, let's say rhymes with gosh. I don't know, whatever. Gosh. I don't know how to spell that word. I think that's it. Rhymes with. But notice that they're actually exponential functions, even though we call them hyperbolic trig functions. They're not trig functions in the sense that we know trig functions. So you do need to know the definitions of hyperbolic sine and cosine, which are those exponential functions. You need to know those. You're not responsible for the graph. And so what we're looking at is, just without all of the development, when we developed circular trig functions, we said, all right, well, here's sine and cosine. What if we looked at the ratio or the reciprocal? What if we added those things together and squared them, get all these identities, right? The same idea is prevalent here with hyperbolic trig functions, but primarily we're focusing on their derivatives and their antiderivatives. So as far as the hyperbolic trig stuff on the exam, it would just be the things we talk about in these notes, and it's a pretty short section. So you're just responsible for a few things. I'll point those out as we get to them. I don't expect you to remember all of the identities for these, or all of the antiderivatives, all of the derivatives. But starting off really basically, we can say, what's the derivative of the hyperbolic sine function? What's the derivative of sinh of x? And the derivative of cosh x. So that's when, at least initially in how we would develop this, once we know the derivative, we know the derivative, right? Like, I know the derivative of whatever trig function is this, but we actually had to go through a formal argument using the definition of a derivative to say that the derivative of sine is cosine, right? It's kind of a similar thing. We could go through the argument that the limit as h approaches 0, find the difference quotient on the hyperbolic sine, try to use identities to do all that, or we could just go off the definition since it's just an exponential function and take the derivative of that, because that's how that function is defined. And the same thing for hyperbolic cosine. The easiest way to compute its derivative, at least initially, until we know what it is to use the definition. Okay. So the half is a constant. We'll take that out of the derivative and divide by 2 after we're done. Derivative of e to the x is e to the x. Derivative of negative e to the negative x is positive e to the negative x over 2. So what is the derivative of the hyperbolic sine? It's the hyperbolic cosine, right? Because e to the x plus e to the negative x over 2 is the definition for the hyperbolic cosine. So there, now we know derivative of sinh is cosh. Do the same thing for the derivative of cosh. Derivative of e to the x. Derivative of e to the negative x. And then our constant over 1/2, or times 1/2. So we see that is sinh. Okay. So we'll come back to that in a minute. Does anyone have any questions about those things? So what exactly is a hyperbolic trig function? The analogy we're gonna make is to the unit circle with our circular trig functions. So back in this setting, so say we had some angle measure here that we call theta. So we're thinking of the unit circle that way. But we know, remember in general, that cosine of the angle was defined as what? Yeah, the opposite over the adjacent, right? So think about it this way. I'm going to draw this perpendicular here to look at that point. X, Y. So cosine of theta in that setting, we said was the x coordinate over the radius. But we're with the unit circle, so the radius is 1, right? So cosine of that angle just gave us the x-coordinate for that point on the unit circle. And similarly, sine theta gave us, it's really y over r again, but r is 1. So it's at any point on the unit circle, xy can be described as cosine theta, sine theta. That's what I want to say. So that then, like when we look at the hyperbolic ones, you'll see this t floating around. Maybe we can sort of connect that to this setting as well. Does anyone remember how to measure this arc length here? The arc length of a sector?
Percentage of the circle.
Yeah. So that length is the radius times theta. But again, unit circle radius is 1, so the length is the angle measure. So another way to think about cosine theta, sine theta is cosine t, sine t on the unit circle. So let me move this. We'll say this is the, oops. I'll say that's the, we'll call that the length of the sector. Does anybody remember how to find the area of the sector?
Find the whole area. And then it's theta over 360 times 4.
So yeah, we want to use radians.
Oh, over 2 pi.
All right, so I didn't catch all of that. So we'll say the area of the sector is capital A, like that. In terms of theta, though, we have 1/2 theta times r squared. For the unit circle, r squared is 1. So the area of the sector is 1/2 times theta. But we already made the connection that theta was t, right? Theta and t are the same thing. In other words, t is equal to twice the area of the sector. So that's another way to think about t. I don't know that this is going to matter all that much, but it's just we're kind of trying to set up parallels between the circular setting and the hyperbolic setting. But the idea was that sine and cosine here describes points of unit circles, on the unit circle rather. The hyperbolic trig functions come from sort of that same reasoning applied to the unit hyperbola, which has the formula opens in the y direction. So y squared minus x squared equals to 1. Sorry, x is positive because it opens in the x direction. That would be the unit hyperbola opening like this. So we'll just switch these two. X squared minus y squared equals 1. So just that's that equation. And note, if we go back up to the equation for the unit circle, that's where that Pythagorean identity comes from, which gave us the other two Pythagorean identities, right? So if I say cosine of theta is x and sine theta is y, then cosine squared of theta plus sine squared theta is equal to 1. Just directly from this relationship in the equation of the circle. So we said really, that was the fundamental identity for our circular trig functions. So we do get a similar identity here, but what we have to look at to make this parallel, we have to look at some point on the unit hyperbola here. Just say that's that. And then so instead of looking at like how we did, we said, well, this point xy on this hyperbola is described by cosine, cosh of t, sinh of t. Instead of the area of the sector, if we look at the area of this region, so the ray connecting the point to the origin and the unit hyperbola, that area is also t over 2, or twice the area is equal to t. We don't really look at like an angle measure here. So instead of thinking about the angle measure in the circular sense, we think about t in the circular sense. T is twice the area of that sector. Here, t is twice the area of this region. And so that's kind of what this T is for here. So the parallels aren't 100% direct because we're not measuring an angle. But if we tie that with the unit circle, we tied that angle back to T, and we said that was the same thing as twice the area of the sector. That's kind of, that's our parallel, really. And so that's what's giving us the points on the unit hyperbola. But just a quick note, since cosh of t was e to the x plus e to the negative x over 2, well, for any value, sorry, e to the t, for any value of t that we plugged in here, what would this evaluate to? What kind of number? In other words, if I plugged in a t, could I get a point over here?
No,
No, how come?
not negative.
This is not negative, right? E to any power is always positive. You add 2 positive things, divide by a positive. So this is always positive. So it's positive for all t. So it's not also direct to the unit circle in the sense that I can get a point in any quadrant on the unit circle by saying just sine cosine, right? Here, since the cosh or the x coordinate of that point is always positive, if we wanted this point over here, let me try to make it a little more symmetric. If I wanted this point over here, then I just have to make it negative. In other words, I just compute cosh of t and then make it negative. Because the hyperbolic sine as e to the t minus e to the negative t over 2. Sometimes that's positive and sometimes that's negative. So that can give us, positive y values here, here, or negative y values here or here. So I think that's worth mentioning as well. No, and notice the further and further we get out in that first quadrant, as far as the point x, y, then we eventually have this, because our unit hyperbola anyways, that thing is following this asymptote. Oops. Like this, and like this. So if we're looking at that area, then we are limited up till we get to that 45-degree angle, if you will. But anyhow, that's sort of the context. We're not going to get too involved with working, or I don't know. I don't know that your book gets too far in detail with that either. But that's kind of what we want to stop with, just to give us some sort of context of where these functions come from. Okay. So certain things we can find now, like sinh plus cosh. We then think about the identity, or rather the definition. If I want to see what sinh plus cosh is, what's e to the x minus e to the negative x over 2 plus e to the x plus e to the negative x over 2. E to the x. You all agree with that? So we have e to the x minus e to the negative x plus e to the x plus e to the negative x all over 2. The e to the negative x's cancel out. You have 2e to the x over 2, which is e to the x. So I don't know, I mean, maybe that's cool, maybe it's not, but we could figure that out. Hyperbolic tangent rhymes with Blanche. So it's tanch. You say either way, tanch or hyperbolic tangent. I don't think there's a universally agreed upon language. But again, the way we would say, well, how is that defined? We could look at sinh over cosh and just figure out that it's e to the x minus e to the negative x over e to the x plus e to the negative x. So that's how we would actually define the hyperbolic tangent. And here's the graph. You're not responsible for these graphs, by the way, so. And then we can sort of start building all of these identities from, you know, the way we did with circular functions. So here's a lot of them.
So as far as the test, how are you going to go over this section, I guess?
You're gonna be responsible for this. You're gonna be responsible for this identity for sure. That's the most fundamental identity to the hyperbolic trig functions. But with this identity, just like with the circular trig functions, we get these two identities. So those two identities there circled are immediate from the fundamental identity. And honestly, you should know the reciprocals too, because they're the same as the reciprocals in the circular setting. But as far as like what would show up on the test, I'm putting those in red here. And I'll do the same thing for the derivative and antiderivative formulas too. So those are important to know. The derivative and antiderivative formulas are these top three really that we should focus on. And honestly, if you know the three derivatives, you know the three antiderivatives. So those three, you should be, or six rather, responsible for knowing how to integrate those things. Yeah?
What are those called, the reciprocal ones?
Oh, this hyperbolic cotangent, hyperbolic secant, hyperbolic cosecant, coth, sech, and cosech. Yeah. I think Lewis Carroll named these things. But does everybody remember, if you know a derivative, how you find an antiderivative?
It's the opposite.
You just kind of reverse engineer that, right? So if I remember, hey, I don't remember how to find the antiderivative of hyperbolic sine, but I do know the derivative of the hyperbolic sine. So you got to at least remember that. The derivative of the hyperbolic sine is the hyperbolic cosine, right? Plus, you know, so that's kind of what we start off working with, and then we say, well, I want to know an antiderivative. So what happens when I take the antiderivative with respect to x on both sides? What's the antiderivative of the derivative with respect to x?
Nothing. The same.
It's the same function, right? Because they're inverses of each other. So this side simply turns into hyperbolic sine. And there we have an antiderivative formula. The hyperbolic sine is the antiderivative of the hyperbolic cosine with respect to x. Of course, we have our constant of integration, but that's the idea. If you know the derivative, you know the antiderivative. Or you can just remember all six. Either way. We'll pick back up here. We only have a few examples, so this probably takes 20-30 minutes to get through, and then we'll talk about our first exam. Scroll up or go back. Okay.